Okay, thank you very much to KARIM for inviting me. I realise I think I'm the last speaker before the break, so I'll not keep you for too long. We're all ready for our coffee. What I'm going to do is give you a brief overview to my work, some of my research work, perhaps take a slightly different direction from some of the recent talks, and we'll go to the top of the planet and look at contaminants in the Arctic and why do we do that. And then I'm going to give some sound bites to my research where I have been involved with a number of companies and looking at the fate of agrochemicals, pesticides in what I would call micro-environments, and I'll give some examples of that. Okay, my research is involved in looking at the environmental fate and specifically the long-range atmospheric and oceanic transport of chemical contaminants. So not just agrochems, but also industrial chemicals as well. I'm involved in looking at the degradation and fate of these chemicals in agricultural environments, and also more recently looking at novel pharmaceuticals in wastewater streams as well. This is my team, and they're divided into those areas. The group at the top there are their research I'm going to talk about briefly now. I've been involved in North American programs with specifically with the Canadians as part of their long-term air monitoring network to look for air toxics across the top of the planet. And the rationale for that, it really is that the Arctic is a barometer for everything that goes on in more southerly regions. Some of these chemicals are persistent. We're certainly interested in many of the legacy persistent organic pollutants like PCBs, DDT, those familiar beasts from the past. And we've had this long-term air monitoring program at a number of sites, specifically at Alert here, but also in the Norwegian Arctic on Mount Zeppelin at Ny-Ålesund, which is a research station. And we've got over 20 years worth of systematic air monitoring data. And in the last 3 to 4 years, the suite of chemicals which they've been screening for has expanded into what we might call emerging chemical contaminants as well. And unfortunately, there are many currently used pesticides which can make it up into that environment. And here's an example of a project that we were involved in that was funded initially through the Canadians, and then later at the time, by a crop science who had the patents for a particular chemical called endosulfan. This busy-looking figure really just shows the time series of endosulfan expressed as a natural log of its concentration in air, and this pink line is a long-term trend, and it goes from 93 to the mid-2000s. And I could extend that for the next 5 years up to current day, and we're not seeing any decline in this chemical. Why is that? Endosulfan is no longer used in Europe, it's no longer used in Canada, so we must have sources from elsewhere. So this is why we do these types of air monitoring programs up in the high Arctic, because it really gives us an assessment of the global pollution status of specific chemicals. And my work, funded largely by the Natural Environment Research Council and also within the EU, we've been looking at the fate of these chemicals, how they deposit into the snow, into the sea ice, and then how they impact the environment. So that was a project which was funded by a crop science, really to interrogate the Arctic data set, look at quality controls, what is the fate of their product in this environment. I must stress Bayer no longer produces chemical, and because of some of this work, it has influenced international legislation. Endosulfan is now included as a persistent organic pollutant, Annex A of the UNEP Stockholm Convention on Persistent Organic Pollutants. So if your product ends up in this environment, it's worth investing in university research to see where this chemical ends up. We can see the accumulation of currently used pesticides in ice cores which have been sampled in the northern reaches of the European Arctic. And that led us on to the work I'm going to talk about now, is looking at the environmental fate and degradation of these compounds. So here we have two chemicals, phenetrathione, methylparathione. They're two organophosphorus insecticides, and you can see this is their light absorption, and you can see how these two chemicals, their absorption actually occurs within the solar spectrum. So they offer interesting chemistry which will dictate their environmental fate. My lab, I've developed a chemical degradation and fate laboratory. It's supported by all the industry standard chromatographic instrumentation, GCMS, LCMS. We have a sophisticated solar simulator fitted with a xenon arc lamp and a range of filters so that we can simulate different aspects of the solar light regime. Some of the work now which I'm going to talk about is specific to the agricultural environment, and we're interested in how pesticides behave in protected environments. These are plastic protected environments. The increase in plastics in agriculture has been enormous over the last 20 years. Something like 80% of the strawberries grown in the UK are now underneath these types of structures. What are the fate of agrochems within these environments? The first thing you notice when you walk into a plastic protected environment is a different light quality. And here we have a figure that illustrates the light irradiance. This is just the light energy expressed in watts per meter squared per second across the spectral range right from the UVC, UVB and A, all the way up to the visible wavelengths. And this is the light regime under different plastics. So we have standard plastic, a UV transparent plastic, and then no film at all. And you can see under the no film that you see transmission of light right the way down to the UVB. Under the plastics, though, we see that the UV transmission can be curtailed. So what effect will that have on pesticides which might be applied to crops within that environment? So here's an example of methyl parathion. I demonstrated that methyl parathion absorbed in the UVB. And here we have a simple degradation, an aqueous degradation done in bespoke quartz glass vessels that were run in our solar simulator. And there's a first order plot. And you can see that under the opaque plastic films, there's no degradation at all. And that matches our control, which is a dark environment. When we look at degradation under the agricultural plastic film, which is UV transparent, then we start to see significant degradation. The message here is that if you're applying your pesticide under plastics which are UV opaque, then your residues on your crop surfaces are going to remain for much longer. So it's easy to jump on a bandwagon to say, residues are going to be higher on those crops which are harvested within plastic protected environments. But there's more to it than that. We can also demonstrate the results for pesticides actually applied not just in an aqueous media, but also applied to lettuce surfaces. And what we are trying to demonstrate and develop is a management tool which could be used by growers or even by agrochem companies to say, well, you don't actually need to apply as much chemical because it's going to be retained or remain within that environment for much longer than under open field conditions. And that's what we're working towards at the moment. Another project, and I'll finish off here, is work that we've been doing with Worldwide Fruits, which are distributors, particularly of hard fruits. So this again is with colleagues at Lancaster, plant biologists. And one of the concerns here is that within pomiculture, you get some of the highest pesticide residues on things like apples and pears. Often apples and pears are transported long distances. You run the risk of fungi and mildews, so they're often treated post-harvest with a range of fungicides. And we did work with Worldwide Fruit to look at two actives, Captan and chlorpyrifos. Captan is a fungicide, chlorpyrifos is an insecticide. And what the goal of this was to demonstrate that we can use different parts of the UV spectrum to degrade those pesticides during the distribution and the processing of apples when they're being graded and sorted and sold onto the market. So what we did, we exposed the pesticide-coated apples to do two different light sources, a UVC lamp, and here's the irradiance of the spectral irradiance of the UVC lamp. It's highly focused with about 240, 250 nanometers, And then the spectral irradiance here of our Atlas sun test, which is much broader. The Atlas sun test here extends down into the UVB, and clearly this lamp here is for the UVC region. And when we look at the results, here we have Captan, which shows quite remarkable degradation in our first time step, which is 30 minutes. So if we were to develop a technology at a sorting and grading plant for apples or pears, then what we need to do is to extend this work to see what's happening in the first few minutes, because during distribution you could hold up your apples under a UVC lamp source for a minute or two, and you may be able to degrade the active substance quite significantly in those first few minutes. So that's where we're up to. And likewise with chlorpyrifos, which shows some absorbance within the UVB, and also specifically as well under the UVC, we see similar rapid degradation. So some horizon scanning. I won't talk about the Arctic. Our plan is, under the plastics work, to develop a user tool which can be used by either agrochem or growers, horticultural growers, so that they can look at pesticide management for any sorts of light conditions and any different types of agricultural plastics which are coming onto the market. Pesticide degradation work in non-standard environments. We're interested in how pesticides can be degraded with the presence of high levels of nitrates and nitrates, and we've published some of that work now, and the development of novel technologies which might be of interest to some of the people here to ensure rapid removal of unwanted pesticide residues on fruit, for example. Okay, thank you very much.